original. Let's see what that means in terms of the familiar property diagrams. Isothermal compression. Compression along an isotherm. Adiabatic compression. Temperature increase to another isotherm. Isothermal expansion. Expansion along this upper isotherm. And finally, adiabatic expansion to bring the temperature back to the original isothermal. And so on. And this area on the PV diagram represents the net work done during a single cycle. But why the Carnot cycle? Well, every thermodynamics course deals with the Carnot cycle, and we're no exception. You see, the Carnot cycle is unique. It's a cycle which theoretically gives the maximum possible thermal efficiency. But because it represents the limit of achievement of thermal efficiency, it is by its very nature an abstract conceptual construction. No real engine based on the Carnot cycle has ever been built. Nevertheless, the Carnot cycle is crucially important because it tells us what is possible and, more importantly, what is impossible in a thermodynamic process. So, how does it do this? Well, we'll start off by calculating thermal efficiency of an engine. Remember, that's the net work output divided by the net heating input. And we'll suppose that this is our engine. And I want you to look, for the moment, just at the energy transfers to and from the engine. There are three. There's the energy transfer by heating to the working fluid, QH, the energy transfer by heating from the working fluid, QC, and the energy transfer by working, the work done by the engine, W. Now, as the working fluid goes through one complete cycle, it returns to its original state, and therefore the net change in internal energy will be zero. So you know from the first law that that means that the net sum of the energy transfers will also be zero, or the work done will be equal to the difference between these two energy transfers, QH minus QC. So now we have a way of calculating the thermal efficiency of an engine. It's just the work output, QH minus QC, divided by the heating input, QH. And if we rearrange that, that comes to 1 minus QC over QH. Now, the engine work output, W, must always be positive. That means that QC must always be less than QH, or the thermal efficiency must always be less than 1. That's true for a heat engine. How much less than 1 will depend on this ratio, QC over QH, of the heat transfers. Now, that expression for thermal efficiency is true for any engine operating over any cycle. So what's so special about the Carnot cycle? Well, let's return to the property diagram for the Carnot cycle. One of the things that's special about the Carnot cycle is that these heat transfers occur only during the isothermal stages. There is no heat transfer during the adiabatic stages, by definition. So we can say the net energy transfer by heating to the working fluid, QH, must occur during this isothermal expansion at a high temperature, TH. And the net energy transfer by heating, QC, must occur during this low temperature isothermal compression at TC. Now, let's return to our engine representation. This time I want you to think about how these heat transfers occur. Suppose now that this is an idealized Carnot engine, and it has available two reservoirs, a hot reservoir and a cold reservoir, which we can bring into contact with the working fluid in order to allow energy transfer by heating to take place. Now the question is, what should the temperature of these reservoirs be in order to achieve this maximum possible thermal efficiency? And the answer is, the reservoir temperature should be exactly the same as the working fluid temperature during the contact. Why? Well, we have to use a thermodynamic thought experiment. We've already seen that if we have two bodies at different temperatures, like these two reservoirs, we can always put in a Carnot engine and extract some work. Now, suppose that this hot reservoir, the temperature of this hot reservoir was higher than the temperature of the working fluid. Then we could use that temperature difference to put in another Carnot engine between the reservoir and the working fluid and produce some extra work. That means that our original Carnot engine can't have been working at maximum thermal efficiency. And we use that kind of thermodynamic argument to show that only when the reservoir is at the same temperature as the working fluid can we achieve maximum thermal efficiency. That's the condition. And this is what Carnot realized when he invented the cycle, that any time that you contacted the reservoir and the working fluid at different temperatures, then you were losing some possibly useful work. Moreover, any temperature change which the working fluid undergoes must occur while the working fluid is in isolation from the environment, that is, during adiabatic processes. The heat transfers have to occur isothermally and, in the limit, with a zero temperature difference. That's what we mean by a reversible process. Any small temperature difference will introduce an irreversibility, and that will reduce the thermal efficiency. So just to sum up, the thermal efficiency, 1 minus QC over QH, for a Carnot engine operating between two isothermals will achieve its maximum theoretical value when QC and QH occur in isothermal and reversible processes. Just one final point. The rate at which that heat transfer occurs does depend on there being a temperature difference. The larger the temperature difference, the faster the heat transfer will occur. Now, in a purely theoretical Carnot cycle with zero temperature difference, you can imagine that this heat transfer process will take forever. Now you can see why the Carnot cycle is a purely conceptual model.
But nonetheless, the Carnot cycle can lead us to ideas that we couldn't get in any other way. Suppose we had an enormous number of Carnot engines, all producing the same work output. That would mean that the difference between the individual QHs and QCs would be the same. And we can use that idea to lead us to an absolute scale of temperature. Now, why would we want that? Well, there are snags with other temperature scales. The temperature scales that we normally use are based on the variation of some material property or other, like the expansion of mercury. But the problem with these scales is that they're not linear with each other. So it would be an awfully good idea if we could leave material properties behind altogether and go for something else. And we can do that with the Carnot engine. From what Tony's told us, it wouldn't matter what the working fluid of the Carnot engine was, or indeed what the reservoirs were. So if I could base a temperature scale on Carnot engines, then I would have a highly desirable and independent temperature scale. You see, temperature scales can be chosen quite arbitrarily. For example, the Celsius scale is 100 equal intervals between the ice and the steam points. But equally, I could have chosen any 2 points and drawn a straight line between them. So let's do that with this Carnot engine. I can call the temperature of this hot reservoir TH, and the temperature of the cold reservoir I can call TC. And I can relate those directly to the energy transfers QH and QC by a linear relationship, so that QC divided by QH I can define as being equal to TC over TH. And that's a perfectly valid way of defining a temperature scale. And what that means is that I can now re-express Tony's efficiency equation in terms of my new temperature scale, so that QC over QH becomes TC over TH. And in this form, the equation can tell me quite a few things about my new temperature scale. For one thing, I know that the efficiency can't be less than 0. And so TC over TH can't be greater than 1. And in turn, that means that TC must be less than TH. And that's very much what I'd expect. The temperature of this reservoir is greater than the temperature of this reservoir. I also know from the first law that the efficiency can't be greater than 1. And that tells me two more things about my temperature scale. If the efficiency is 1, then it's a limit, a maximum. And TC over TH must therefore be 0. That can happen in two ways. Either TC is 0 or TH is infinite. Now, if TH is infinite, then there is no limit to my temperature scale. If, on the other hand, TC is 0, then there is a lower limit, an absolute 0. So what I have here is an absolute scale of temperature that has nothing to do with properties. The temperature intervals between each reservoir are the same. There's no upper limit, but there is an absolute 0.
So, where have we got to? We've seen that an idealized engine, using the Carnot cycle, can achieve a maximum possible thermal efficiency. And that thermal efficiency will depend only on the absolute temperatures of the hot and cold reservoirs. But maximum thermal efficiency isn't everything. An engine designer would also be interested in maximizing the net work output from his engine. If we return to the property diagram, you remember that the net work output is just given by this enclosed area. In the case of a Carnot cycle, the area between the isothermal stages and the adiabatic stages. So if we wanted to increase the net work output, then we would be looking to increase this area. And if we wanted to do that between the same two isothermals and over the same overall volume change, then we might be looking to somehow pulling these lines apart a bit. And that's exactly what happens in the Stirling cycle. Just like the Carnot cycle, the Stirling cycle has 4 stages. The first stage is an isothermal compression process. Energy transfer by heating occurs at constant temperature. The next stage is a constant volume process. Energy transfer by heating occurs as the temperature and pressure of the working fluid rises. With the gas fully compressed, the return to the starting state follows in 2 stages. First, an isothermal expansion, then a constant volume cooling. If we compare the net work output of the Carnot cycle with the net work output of the Stirling cycle, we can see quite clearly that operating between the same 2 isotherms and over the same overall volume change, that the Stirling cycle, the net work output, is much larger than the Carnot cycle work output. You can see that clearly from the difference in the enclosed areas. So the Stirling cycle work output is larger than the Carnot cycle. But is the Stirling cycle as thermally efficient as the Carnot cycle? Well, no. Because during these constant volume processes, energy transfer by heating occurs while the temperature of the working fluid changes. And we've seen already that that is an inherently irreversible process and therefore causes a drop in thermal efficiency. Nevertheless, the Stirling cycle is worth looking at further from a practical standpoint. As I said earlier, no one has yet built a true Carnot engine. But Stirling engines have been built, and with thermal efficiencies closely approaching the maximum thermal efficiency of a Carnot engine. And this is done by incorporating an internal heat regenerator. which exchanges the heat from one constant volume process to the other in the Stirling cycle. So let's take a closer look at some of these real engines.
There's an enormous variety of Stirling engines with a wide range of configurations, but we've picked this particular demonstration model because it's fairly easy to see what's going on. Up to now, we've been working purely in theoretical terms and haven't considered the nature of working fluids at all. But here, we're working with a real engine with a real working fluid. It's a fixed mass of air whose volume varies with the movement of the working piston in this cylinder. The function of this bit here, called the displacer, is to act as the regenerator that Tony was talking about. It's important, and I'll say more about it in a moment. But meanwhile, have a look at the whole cycle. This is the working fluid at the cold temperature Tc. So first there's the compression stage, followed by constant volume heating, then expansion, and finally constant volume cooling. This is what happens to the working fluid. So how is this brought about? The working piston compresses the cool gas to its minimum volume, and since the piston was doing work on the fluid, so energy needed to be removed to maintain isothermal conditions. Next, the hot regenerator moves through the working fluid to raise its temperature, the total volume of the fluid remaining constant. The pressure is now higher than the outside pressure, and so the gas can now do work on the piston. Isothermally, of course, it's a Stirling cycle. So energy must be transferred to the fluid by heating. And finally, to drop the pressure back to the original pressure, the temperature of the fluid must be reduced at constant volume. The regenerator does this. It stores the energy of the fluid, which it can then use for the other constant volume process. Look at that again, this time paying particular attention to the action of the regenerator. Isothermal compression, constant volume heating from the regenerator, isothermal expansion, constant volume cooling to the regenerator. The successful functioning of the regenerator is absolutely crucial to the success of the Stirling engine. In fact, there's a whole order of magnitude difference between the thermal efficiency of an engine operating on the Stirling cycle with a regenerator and without. Needless to say then, the development of effective regenerators has been exercising many fine minds over the last 20 years or so. Tony's already shown you the ideal pressure volume diagram for the Stirling cycle. Here's the reality. This is the PV diagram for our engine. Compare that with the ideal, the constant volumes and the isothermals. And remember that this area here represents the work output during one cycle. At the moment, it's working against this load here. Take the load off, and the area gets pretty small. Any area there is represents work done against internal friction. Well, there's enormous potential in this sort of engine. New materials techniques have meant more effective regenerators are now possible, and that has opened up a whole range of possible applications. Here's one exciting example. Most lorries are powered by diesel engines, but this one's an exception. In this prototype, the diesel engine has been replaced by a Stirling engine, and in tests, the efficiency of the engine has been found to be comparable with the diesel engine. So what are the essential differences between this and a diesel engine? Let's have a closer look. The most obvious feature of a Stirling engine is this huge combustion chamber. The working parts are mounted underneath. You remember from the studio model that in a Stirling engine, the working fluid is entirely separate from the hot and the cold reservoirs. The working fluid goes through the Stirling cycle, following the route that you're familiar with from the PV diagram. The hot reservoir is provided by the combustion chamber, and the cold reservoir is provided by cooling water underneath there somewhere. The important thing is that it's just the control mass in the cylinder that undergoes these pressure and volume changes. The control mass stays there. And that's quite different from a diesel engine, where a fuel-air mixture is introduced into the cylinders, exploded, and then it's exhausted. And so the working fluid is continuously changing. And the difference is quite crucial to the Stirling engine, where combustion is continuous and therefore more complete. And that means less unburned pollutants and a cleaner exhaust.
Stirling engines aren't just confined to motor vehicle applications. For example, this generator set for underwater applications is powered by a Stirling engine. Again, notice the characteristic dome of the combustion chamber. In this case, the chamber's been removed, and that'll give us a chance to see the all-important regenerators. Krista Bratt is a development engineer for United Stirling in Sweden.
Here you can see a cut-through of a regenerator house, same as this one here, and there are several layers of mesh sintered together, and the regenerator looks rather simple when it's designed like this, but it has been optimized very carefully, and it's a compromise between fluid friction, dead volume, heat transfer area, and things like that. And it has a very high efficiency really here, which is also a necessity in order to achieve the high efficiency of the Stirling engine. And I think the energy that is going out and in the regenerator is about 4 times the heat that is generated in the combustor. So it has a tremendous heat transfer capacity, the regenerator. And if we didn't have the regenerator, of course you could imagine that working fluid 700 degrees centigrade should enter directly into the cold area, and that would be a tremendous loss, as the efficiency is really dependent on having a small temperature difference between the fluid and the heat exchanger all the time.